All right, this should be a relatively quick video, but we'll finish up here with precipitation and separation of ions. Now, we have to look at the reaction quotient Q and compare that to our solubility product constant, KSP. That will answer the question, will this solution precipitate a solid or won't it? So obviously, three possibilities. If Q is greater than KSP, we're going to get a precipitate. If Q is equal to KSP, then we are at saturation. We're right on the verge of precipitation. And if Q is less than KSP, then no precipitate will form because we're not at saturation yet. Now, part B says the KSP for barium sulfate is 1.1 times 10 to the minus 10th. Predict whether or not a precipitate will form in each of the following situations. Now, if I'm going to mix 25 milliliters of 2.0 times 10 to the minus 4th molar barium nitrate and 25 milliliters of 1.0 times 10 to the minus 4th molar sodium sulfate. Well, that sounds like a lot going on. We can do this double replacement reaction and see that although both barium nitrate and sodium sulfate are soluble, when I react these two, I'm going to get sodium nitrate, which is soluble, but barium sulfate, which is not or may not be soluble. So here's my relevant equilibria. And when I sit down to actually crunch the math, I've got to do some calculations here. I've got to find out, well, what is my concentration of barium ions and what's the concentration of my sulfate ions? And I can take the volume times the molar concentration and find out the concentration of each of those two ions. And my total volume is, of course, 50 milliliters because I've mixed the two solutions together, so 0.050 liters. So I can take my two quantities, my number of moles, divide it by my volume and get molar concentrations, plug that into my expression to compute my current value of Q, and when I do, I see I have 5.0 times 10 to the minus 9th. Now, I can see that my Q is now larger than my KSP, so I'm going to get a precipitate that's going to form. Well, now let's look, of course, at the other situation where I have a KSP for the same barium sulfate. Now I'm going to mix 75 milliliters of barium chloride with 75 milliliters of potassium sulfate. And I'm going to need to see, okay, what is my relevant equilibrium that I need to concern myself with? And of course, it's going to be barium sulfate because my other possibility of potassium is potassium chloride, which would be quite soluble in water. So here's my equilibrium. And again, I run through the same sort of calculations. I take my volume times my molar concentration, divide that by my new total volume, which is 150 milliliters or 0.150 liters, and I get 25 times 10 to the minus 6 molar for barium ion. I do the same sort of calculation for sulfate, and I get 1.5 times 10 to the minus 5. I multiply these two together to see what my value of Q is. Now I see that my Q is less than my KSP, and therefore I don't get a precipitate that forms. All right, now we have a beaker which contains a liter of a solution in which both calcium ions and barium ions are present. And in this solution, they are both equal to each other at 2.0 times 10 to the minus 4th. And I'm slowly pouring in sodium fluoride. And they give us two different KSPs, one for calcium fluoride, one for barium fluoride. And they're asking us which one will precipitate first and why. So what we've got to do is come up with an answer. Calcium fluoride will precipitate first because its KSP is closer to 0. It has a smaller KSP. You can see, in fact, that's roughly 100,000 difference. As we mix in this sodium fluoride, we're going to cross the KSP threshold for calcium fluoride before I get to barium fluoride. So I want to calculate the minimum concentration of fluoride required in order for this answer to form a precipitate. So I have calcium fluoride. That's going to be my equilibrium reaction. I compute my calcium ion concentration, and I know my KSP is 3.9 times 10 to the minus 11th. So now I can compute my fluoride concentration. And when I do, I get 4.4 times 10 to the minus 4th molar. That's the minimum concentration I need to cause a precipitation of calcium fluoride. If I did the same calculation for barium fluoride, I would get 9.2 times 10 to the minus 2nd, which is about 200 times the same amount. Now, the last part here is to calculate what is that minimum volume of sodium fluoride required in order for this salt to form a precipitate. Well, I know that that concentration is 4.4 times 10 to the minus 4th molar, and that needs to come from, to give us this information, that needs to come from a 0.1 molar solution. So 4.4 times 10 to the minus 4th moles per liter times 1,000 milliliters divided by my 0.1 moles tells me I need to add 4.4 milliliters. All right, that concludes this last video. We'll do a bunch of problems over the course of the next week or so to familiarize ourselves with how this is going to work.